In this video, we will be covering Chapter 11, Section 4, the fundamentals of probability. The first type of probability we'll cover is the theoretical probability. It says, in an event, we'll call that event E, remember that this is called the cardinal number. If you go back to our first unit, a cardinal number is a set that is represented by this particular notation, and it's the number of distinct elements in that particular set. Okay, this is from Chapter 2, Section 1, page 5 of our notes. Okay, so the cardinal number is the likely outcomes, the number of possible outcomes within that set. And its sample space is called S, and it has equally likely outcomes. The probability of event E occurring is going to be the number of outcomes of E divided by the total number of outcomes. Experiment is any occurrence for which the outcomes is uncertain. So if I wanted to say that we're going to roll a dice, we don't know what number the dice will land on. So we'll call that an experiment. Our sample space is the set of all possible outcomes of that experiment. Well, if I'm rolling a dice, the possible outcomes would be the numbers between 1 through 6, including 1 and including 6. The event, which we call E, is the subset of the sample space. In this case here, we call the event tails, and the sample space would be the number of outcomes. So we could have a heads if we flip a coin, or it could be a tail if we flip a coin. The probability of being tails is going to be tails divided by the number of outcomes possible, in this case heads or tails. The cardinal number of that event would just be 1, and there's 2 possible outcomes. So we have a 50-50 chance of getting tails. Let's look at example 1. It says a die is rolled once. Find the probability of rolling part A and number 2. So when you roll a dice, the sample space would be the numbers 1 through 6. The cardinal number of rolling a dice would be 6. Remember, that's the physical number of possibilities. We have 6 options. The cardinal number for the sample space would be 6. The probability of rolling a 2, well, when we roll a dice, there's only one way we can get a 2. So our event would be getting a 2, and the cardinal number would be 1. So if we wanted to know the probability of getting a 2, we would say it's 1 out of 6. Part B says, what is the probability of rolling a number less than 4? So here the first thing we're going to do is our sample space does not change. It stays the same every time we roll a dice. But the event will change. If our event now is a number less than 4, then we have to determine what events would make that true. In this case, rolling a 1, 2, or 3 would mean that the number is less than 4. So if we have an event where 1, 2, or 3 can be rolled, then the cardinal number of this event would be 3. So our probability would be 3 divided by the cardinal number of the space, which is 6. The probability of the event in rolling a number less than 4 would be 1/2 or 0.5. Part C says rolling a number greater than 7. Well, in this case, if we're rolling a dice that is between 1 and 6, getting a number greater than 7 would be an empty set. Remember, we notate it like this. The cardinal number of that event is going to be 0. So the probability of rolling a number greater than 7 would be 0 out of the sample space of 6, which would give us a 0 probability. Part D says rolling a number less than 7. So the event enrolling a number less than 7 would include 1, 2, 3, 4, 5, and 6. Since 6 is less than 7, that would also be included. The cardinal number in this case is going to be 6. So the probability of rolling a number less than 7 will be 6 out of 6, or in other words, 1. A couple of things that you should know on this is you will never get a number less than 0. In other words, there are no negative probabilities. And you will never get a number greater than 1 because 1 represents 100%. Number 2. Number 2 says you are dealt 1 card from a standard 52 deck. Find the probability of getting an ace. In this particular case, you will have in your reference sheet a standard deck of playing cards that have the pictures, and it has the information that you need here. So clubs, spades, hearts, diamonds. These are your aces, jacks, queens, and kings. These are called our face cards over here. You can use this on your exam. Okay. On the other side, I also have the sum of dice that you can use as well. Okay. So just like we did before, I usually keep this in a sleeve so that way I can mark the cards that I'm looking for, and then it's easily erased when I want to start a new problem. Okay, so I suggest that for you as well. All right, let's go ahead and look here. It says, find the probability of getting an ace. So if I'm looking at my cards here, I'm going to go ahead and say, these are all my aces, and how many aces do I possibly have? Well, as you can see, you have 4 aces. And here I just drew the events of how that can occur. A of hearts, A of clubs, A of spades, and A of diamonds. There are 4 cards. If we have 4 cards in the event out of 52, we can say that the probability of getting an ace is 1 out of 13. Make sure to represent this as a fraction or a decimal as indicated on your question. So 4 out of 52 is this. Anytime it's a repeating decimal, see if it's possible to go ahead and change that into a fraction. In this case it is, and that's what we want to go ahead and use. The next question says, Part B, find the probability of getting a red card. So when looking on here, you can see that I have the red and the black cards. If I want the probability of getting a red card, it would be any of these cards here. In this case, we can have 13 hearts, or we can have 13 diamonds. That means the cardinal number for this event would be 26. The cardinal number of the event, 26, divided by the cardinal number of the sample space of 52, it means that we have a 1/2 or 0.5 probability of getting a red card. Part C. Part C says, what is the probability of getting a red king? Again, I'm going to use my cards here, and I'm going to see that if I want a red king, I would have either a king of hearts or a king of diamonds. In this case, our cardinal number of having a red king would be 2. So 2 divided by the cardinal number of the sample space of 52 means there's 1/26 probability of getting this event. Problem 3. If each parent carries one cystic fibrosis gene, find the probability that their child will be a carrier of the disease that is not actually sick. So in genetics, the children often get one gene from each parent. In this particular case, the little c is the defective gene, or the gene of having cystic fibrosis. The capital C is a normal gene. So if the first parent is a carrier, that means they have one normal gene and one defective gene. The second parent is also a carrier, so they have a capital C and a lowercase c. For the children is going to be they can inherit a normal gene from each parent, which is identified as a CC, which means that they're not sick and they're not a carrier. It could be a capital C with a lowercase c, which means that they're not sick and they are a carrier for their children. It could mean that they get a defective gene from the first parent and a normal gene from the second parent, which in that case it also means they are not sick and they become a carrier for their children. Or they can get the cystic fibrosis gene from both the first parent and the second parent, which means that they are sick and they are still a carrier. So what is the probability that the child will be a carrier of the disease but not actually sick? Well, our sample space is these four options. Since our sample space is these four options, then we want to look at the cardinal number of the event occurring if the child is not sick but is a carrier. We see that there's two ways that this can happen. So the probability of being a carrier but not sick is going to be 2 out of the 4. In other words, it's half. They have a 50% chance of not being sick but will be a carrier. The empirical probabilities. Empirical probabilities are events that are not likely equal and are calculated strictly by observations. An example for this would be, let's say, what is the probability that an intersection is going to have an accident? Not all intersections are going to have the same probability of having an accident because of different types of factors, such as the type of control that's in an intersection. For example, is it a roundabout? Does it have stop signs? Is there a traffic light? It also depends on the number of vehicles traveling through the intersection. It could also include, is there pedestrians? Is that an area where bicycles are allowed to go through as well? So there's a lot of different factors that intersection is going to have an accident. So we'll be talking about those types of probabilities. So on this next page, you will see here we have the Meredith status of the populations for people who are 15 years or older in millions. What we did here was break down their gender, male and female, and then we asked them if they were married, never married, divorced, or widowed. So out of all the people who were asked, 66 million were males who were married. 67 million were females who have been married, and then so forth. One of the things that you want to do when you have a table like this is make sure that it has the total for each row, as shown here, and for each column. The total population will be right here at the bottom right column. All of these people who are married, never married, divorced, or widowed need to equal the amounts of male and female participants. So in this column, in this space here, if you add up all of these, it comes out to 254 million. And if you add up all of these, you also get 254 million. This is a really great check to make sure that you've added them correctly. Let's look at the first part. It says, if one person is randomly selected from the population, describe the probability to the nearest hundredth. So now we're wanting 2 decimal places that the person is divorced. Well, I have the exact same table in my cover sheet here because we're going to be doing several of these problems. Since we are looking for people who are divorced, I'm going to go to the divorce column and go ahead and circle that. Now, notice in this case, I'm only circling the people who are divorced, and I didn't care if it was a male or female, so I'm going to go ahead and circle both of these columns. I didn't do this one because I don't want to accidentally add this when I'm adding everything at the bottom. So if you can see here, I have the number 26. Yes, it's in millions. Don't worry about that, because remember, when you're talking about probabilities, zeros will cancel out with the zeros for the total population. So, and then again, you need the total always in the denominator, which is the 254. So when I put this in the calculator, you get all of these numbers. Now remember, when you're rounding to the hundredths place, you're going to look at the thousandths place, which is the third decimal place. If this number is greater than 5, you're going to round the hundredths place up by 1. Since this is a 2, you're just going to leave this at approximately 0.10. One of the things you need to be careful with is if you enter just a 0.1 or homework, it may count it incorrect because you did not put 2 decimal places. If this happens, I'll still give you credit for it, but you may have to forward that information to me. But try to make sure you enter in 2 decimal places. If it's a 0 there, go ahead and just put a 0 on your homework. For part B, it says, what is the probability that the person that is randomly selected is female? Well, we need to know how many females we have, so I'm going to go to the female section, and we're counting all of them in every single one of these categories because all of these are just females. So here I have a total of 131 females, which I have here, and then again divided by the total number in the entire group, which is 254. As you can see here, I went ahead and wrote it out to 3 decimal places because you want to find the probability to the nearest hundreds. Since the third decimal place is a 5, we're going to take the hundredths place and add a 1 to it. So we get approximately 0.52. On part C, it says, what is the probability that the person selected has never been married? So in that case here, we're going to go to our never married category, and it doesn't specify if it has to be a male or a female, so we're going to go ahead and circle both of them. As you can see here, the total number of people who are never married is only 81. So I'm going to have that in the numerator divided by the total population, which is in this case 254. Go ahead and write the decimal out to 3 decimal places, and as you can see, the third decimal place is greater than 5, so we're going to add a 1 to the hundredths place. So here, the probability that the person selected who has never been married is going to be a 0.32, or in other words, about 32%. Part D says, what is the probability that the person selected is male? Well, that's very similar to our female scenario. We're going to go ahead and look on our table and see that all of these people are male. The total is going to be 123. So that's going to go in the numerator, and we're going to divide it by the total number of people in the population, which is 254. So go ahead and write that out to 3 decimal places. You'll get in your calculator 0.484. Since the third decimal place is less than 5, we're going to keep the hundredths place exactly the same. So the probability of selecting one person from this study, and that person is going to end up being male, will be approximately 0.48 or 48%. So that concludes the lesson on 11.4, the fundamentals of probability. Let me know if you have any questions.